Hi, I welcome you all to this lecture on quantum interference effects. I'm Dr. Yunus Jerusha, who's about to enlighten you on this. Quantum mechanics took the world of physics by storm, phase by phase. But a paper by Richard Phillips Feynman changed the domain of computer science and the relationship between physics and computer science forever. This paper was on the double slit experiment and demonstrates the fundamental aspect of the quantum world. Welcome to the quantum realm. The beauty of quantum mechanics is that it is counterintuitive, and its journey begins with the double slit experiment. What needs to be done is take a source of light and let its light shine through two identical and very thin slits, and the resultant light falls on the subsequent screen, forming patterns. With this, we need to prove the same physical system can exhibit, under different circumstances, either particle or wave-like properties, otherwise known as wave-particle duality. Light has perplexed scientists and all those with scientific inquisition. Isaac Newton believed it to be a stream of corpuscles or particles, and Maxwell showed its wave-like properties, where waves exhibit interference whereas particles do not. It was Einstein who, however, sealed the deal in 1905 with a photoelectric effect, which showed that photons, or the particles of light, possess both wave and particle-like properties, where when particles exhibit interference, they are behaving like waves based on de Broglie's hypothesis. This experiment is said to illustrate the essential mystery of quantum mechanics. This mystery is embodied in the apparent ability of a system to possess properties which, from a classical physics point of view, are mutually contradictory. The experiment will be considered in three forms and performed with macroscopic particles, waves, as well as with electrons. The first two experiments merely show what we expect to see based on everyday experience. It is a third which displays the counterintuitive behavior of microscopic systems, and it exhibits a peculiar combination of particle and wave-like behavior which cannot be understood in terms of the concepts of classical physics. The macroscopic particles we consider here are bullets which are fired from a machine gun. The result of the firing of bullets at the screen when only one slit is open is seen here. The curves P1 of x and P2 of x give the probability densities of a bullet passing through slit 1 or 2 respectively and striking the screen at x. When both the slits are open, this is what occurs. The bullets accumulate on an observation screen, forming two small piles opposite each slit. The curve P12 of x represents the probability density of the bullets landing at the point x on the observation screen. Let us look at this in a much more detailed manner. Imagine an experimental setup in which a machine gun is spraying bullets at the screen, in which there are two narrow openings or slits which may or may not be covered. Bullets that pass through the openings will then strike a further screen, or the detector or the observation screen behind the first, and the point of impact of the bullets on the screen are noted. Suppose in the first instance that this experiment is carried out with only one slit opened. Let us say slit 1. A first point to note is that the bullets arrive in lumps. That is, every bullet that leaves the gun arrives as a whole somewhere on the detection screen. Not surprisingly, what would be observed is the tendency for the bullets to strike the screen in a region somewhere immediately opposite the position of the open slit. But because the machine gun is firing erratically, we would expect that not all the bullets would strike the screen in exactly the same spot, but to strike the screen at random, though always in a region roughly opposite to the open slit. We can represent this experimental outcome by a curve P1 of x. If we were to cover this slit and open the other, then what we would observe is the tendency for the bullets to strike the screen opposite this open slit, producing a curve P2 of x similar to P1 of x. These results are indicated in the figure shown. Finally, suppose that both slits are opened, we would then observe the bullets would sometimes come through slit 1 and sometimes through slit 2, varying between the two possibilities in a random way, producing two piles behind each slit in a way that is simply the sum of the results that would be observed with one or the other slit opened. That is, P12 of x is equal to P1 of x plus P2 of x. The second experiment is performed with waves. The result of directing the waves at a screen when only one slit is open is shown here. The curves I1 of x and I2 of x give the intensities of the waves passing through slit 1 or 2 respectively and reaching the screen at x. They are just the central peak of a single slit diffraction pattern. When both the slits are open, what we observe on the screen is the usual two-slit interference pattern. The experiment is seen in a detailed manner here. For definiteness, let us suppose that the waves are light waves of wavelength lambda. The waves pass through the slits and then impinge on the screen, where we measure the intensity of the waves as a function of position along the screen. First, let us perform this experiment with one of the slits open and the other closed. The resultant intensity distribution is then a curve which peaks behind the position of the open slit, much like the curve obtained in the experiment with bullets. Let us call this curve I1 of x, which we know is just the square of the amplitude of the wave incident at x and originated from slit 1. Now, close the slit and open slit 2. Again, we get a curve which peaks behind the position of the open slit 2, and let us call this intensity curve as I2 of x. These two outcomes are illustrated. Next, we open both the slits. What results is a curve on the screen, I12 of x, which oscillates between maxima and minima, which is actually an interference pattern as illustrated. It is certainly quite different from what was obtained with bullets, where there was no interference involved. Moreover, the detector does not register the arrival of individual lumps of wave energy. The intensity can have any value at all. We now repeat the experiment for a third time, but in this case we use electrons. Here we imagine that there is a beam of electrons incident normally on a screen with the two slits, with all the electrons having the same energy E and momentum P. The screen is a fluorescent screen, so that the arrival of each electron is registered as a flash of light, the signature of the arrival of a particle on the screen. Let us suppose that the electron beam is made so weak that only one electron passes through the apparatus at a time. What we will observe on the screen will be individual point flashes of light, and only one at a time, as there is only one electron passing through the apparatus at the time. In other words, the electrons are arriving at the screen in the manner of particles. That is, they are arriving in lumps. If we open slit 1 and close slit 2 and observe the result, we see a localization of flashes in a region directly opposite to slit 1. We can count up the number of flashes as in the case of the bullets. We will call this as a result P1 of X. Now do the same with slit 1 closed and slit 2 opened. The result is a distribution described by the curve P2 of X. These two curves gives, as in the case of bullets, the probabilities of the electrons striking the screen when one or the other of the two slits are open. But as in the case of the bullets, this randomness is not seen as all that unexpected. The electrons making their way from the source through the slits and then onto the screen would be expected to show evidence of some inconsistency in their behavior, which could be put down to, for instance, slight variations in the energy and direction of propagation of each electron as it leaves the source. Now, open both the slits. What we notice now is that these flashes of light do not always occur at the same place. In fact, they appear to occur randomly across the screen. But there is a pattern to this randomness. If the experiment is allowed to continue for a sufficiently long period of time, what is found is that there is an accumulation of flashes in some regions of the screen and very few or none at other parts of the screen. Over a long enough observation time, the accumulation of detection of flashes forms an interference pattern, a characteristic of wave motion, that is, in contrast to what happens with bullets. So, we are forced to conclude that this is the result of the interference of two waves propagating from each of the slits. One feature of the waves, namely their wavelength, can be immediately determined from the separation between the successive maxima of the interference pattern. To our electron apparatus, we add a very strong light source placed behind the wall and between the two slits as shown in the figure. We know that electric charges scatter light. So when an electron passes, however it does pass on its way to the detector, it will scatter some light to our eye and we can see where the electron goes. If, for instance, an electron were to take the path via hole 2 that is sketched in the figure, we should see a flash of light coming from the vicinity of the place marked A in the figure. If an electron passes through hole 1, we would expect to see a flash from the vicinity of the upper hole. If we get light from both places at the same time, it is because the electron divides in half, which is incomprehensible. We could imagine that the electrons determine the separation between the slits by supposing that they split up in some way, but then they will have to subsequently recombine before striking the screen. Since All that is observed is single flashes of light. So what comes to mind is the idea of the electrons executing complicated paths that perhaps involve them looping back through each slit, which is scarcely believable. The question would have to be asked as to why the electrons execute such strange behavior when there are a pair of slits present, but do not seem to when they are moving in free space. There is no way of understanding the double slit behavior in terms of the particle picture only. We must conclude that when we look at the electrons, the distribution of them on the screen is different than when we do not look. Perhaps it is turning on the light source that disturbs things. It must be that the electrons are very delicate and the light, when it scatters off the electrons, gives them a punch that changes their motion. We know that the electric field of the light acting on the charge will exert a force on it. By trying to watch the electrons, we have therefore changed their motions. That is, the punch given to the electron when the photon is scattered by it is such as to change the electron's motion, and that is why we no longer see the wavy interference pattern. You may be thinking, don't use such a bright source. Turn the brightness down. The light waves will then be weaker and will not disturb the electrons so much. The first thing we observe is that the flashes of light scattered from the electrons as they pass by does not get weaker. It is always the same sized flash. The only thing that happens as the light is made dimmer is that sometimes we hear a click from the detector but see no flash at all. The electron has gone by without being seen. As we turn down the intensity of the light source, we do not change the size of the photons, only the rate at which they are emitted. That explains why, when our source is dim, some electrons get by without being seen. When we do not see the electron, no photon disturbs it. But when we do see it, a photon has disturbed it. There is always the same amount of disturbance because the light photons all produce the same sized effects, and the effect of the photons being scattered is enough to smear out any interference effect. If we want to disturb the electrons only slightly, we should not have lowered the intensity of the light. We should have lowered its frequency reciprocally, increasing its wavelength. Let us use light of a longer wavelength, red color, or greater than that. We could even use infrared light or radio waves like radar and see where the electron went with the help of some equipment that can see light of these longer wavelengths. If we use gentler light, perhaps we can avoid disturbing the electrons so much. Let us try the experiment with longer waves. We shall keep repeating our experiment each time with light of a longer wavelength. At first, nothing seems to change. The results are all the same. We must remember that due to the wave nature of the light, there is a limitation on how close two spots can be and still be seen as two separate spots. This distance is of the order of the wavelength of light. So now, when we make the wavelength longer than the distance between the two holes, we see a big fuzzy flash when the light is scattered by the electrons. We can no longer tell which hole the electron went through. We just know it went somewhere. And it is just with light of this color that we find that the punches given to the electron are small enough so that P12 prime begins to look like P12, that we begin to get some interference effect. And it is only for wavelengths much longer than the separation of the two holes we have a chance of telling where the electron went. That is, the disturbance due to the light gets sufficiently small that we again get the curve P12 as depicted in the previous slide. The double slit experimental results are as follows. If we look, the electrons definitely go through one slit or another, which is a property that we expect particles to possess. Then results in the electrons behaving as particles do and a line pattern is formed. If we do not look, then we are left with the uncomfortable thought that in some sense each electron passes through both slits, resulting in the formation of an interference pattern, the signature of wave motion. Thus, the electrons behave either like particles or like waves, depending on what it is that is being observed, a dichotomy that is known as wave-particle duality. Some of the applications are used in superconducting quantum interference device, also known as the SQUID, in quantum cryptography, and also in quantum computing. To summarize whatever we saw just now, before observation, matter wave spreads over space and time, whereas during observation, matter wave collapses to a particle state, creating a concrete reality. Kindly think over this. For any further clarifications, click on the link below. Thank you for your patient listening.